Here we come to the last paper of science that we're going to do, at least for this year. And this is physics, which is my jam. That's my stuff, okay? I love physics. That's what my degree's in. I am a big fan of it, absolutely. Although I understand why a lot of people hate it. Completely understand too. But hopefully, I actually think that I could do the best explanations for this subject, because I find that it's not just conceptually kind of knowing stuff. You have to actually understand it in order to answer some physics questions. It's not all memory, which is why, I feel like I can be a bit more useful on this. But without further ado, let's just get straight into it. Again, the link to the paper is going to be in the description in case you want to follow along or use this as a mark scheme or whatever you want to do. Here we have figure 1 showing a stretched spring, and the spring is elastically deformed because we're hanging a mass from it. So I'm thinking like Hooke's law, I'm thinking about those kinds of things. And it says here, what is meant by elastically deformed? So this is basically just one of your definitions that you're going to do. So remember, elastically deformed is whenever you have something that's stretchy and you stretch it, you change its shape by doing that. So in this case, it says, as the force on the spring increases, the length of the spring increases. That's Hooke's law, that's not elastically deformed. Only a very force, so let's actually cross these off as we go along. Only a very small forces need to stretch the spring. The force on the spring causes it to change shape. It could be that, maybe. The spring will return to its original length when the force is removed. So there's two different types of deformation we talk about. We talk about, well, technically a few others, but we talk about plastically deformed and elastically deformed. Technically you have permanently deformed, but let's leave that. The key thing about elastic, think about an elastic band. When you apply a force, if you were to let go, it returns to its original shape. That's what an elastic thing is. A plastic thing, I can deform it, but it won't spring back to its original shape. So for example, if I get a kind of, maybe a can, right, like a can of Coke or whatever, I can crush it, I can plastically deform it, but it's not elastically deformed because when I let go, it doesn't ping back into the shape of a can, does it? So other things that are like elastically deformed, mainly things like springs, okay? Or anything with some kind of bounce to it. So like a rubber ball is also a pretty good one to use. So in this case, it's going to be the last one. The spring will return to its original length when the force is removed. For part 2, it says describe a method to determine the extension of the spring. So if you're lucky, you've done this experiment in school already. But the way you determine extension, if you think about this kind of setup, right? We have this original spring, right? And then afterwards, when we hang a mass, its length changes, okay? So we can't measure that extension easily, directly. But what we can do is measure the length of the original spring. So measure the original length, measure the new length. So let's just call it, ln for new length. The difference in these two values is going to be my extension. So that's why you have the ruler hanging up next to the spring. You take the original length, you then hang a mass on it, write down the new length, and then take the difference between them. So how do we write that in words so we can get the full marks? Well, the first thing is you measure the original length of the spring. Measure original length of spring. And then measure the length after. So measure, you can call it the extended length. Measure, I don't know why, but there's like an E button on my graphical pencil. I really don't know why. But anyways, measure the extended length, and subtract original length, to get extension. So for part 3, it says the extension of the spring is 80 millimeters. The spring constant is 40 newtons per meter. Calculate the elastic potential energy of the spring. Use the physics equation sheet for 3 marks. This is a lot of marks for a question that's not too bad. The equation that you're looking for is that energy is equal to a half times the spring constant times the extension squared, which is sometimes given as an E, or it can be given as a delta x instead. Either way is completely fine. So sub in those numbers, a half, then it's 40. And then what about extension? Well, if you look at my spring constant, it's newtons per meter. So you need to make sure your extension is in meters. So how do you do that? Well, how many millimeters are in centimeters? How many millimeters are in a centimeter? there's 10, so divide by 10 gives you 8 centimeters. And then how many centimeters are in a meter? 100, so divide by 100, you get 0.08 meters. So let's put that all in, whoops, don't forget the other 0, squared. And then let's type it all into our calculator. So instead of a half, I can put 0.5, but let's just do a half times 40 times 0.08. That gives me an answer of 0.128 joules, which is a very small amount, but that should hopefully make sense because there's not much going on with this. In the next question, it says, write down the equation which links extension E, force, and spring constant. This is Hooke's law. So that is going to be F is equal to KE. Again, sometimes they use X for extension instead, but whatever they use, it's all the same thing, okay? So it's just Hooke's law. And for part 5, it says a force of 300 newtons acts on a different spring and it extends by 0.4 meters. Calculate the spring constant. So all we're trying to do here is using this equation at the top, so F equals KE, to work out K. So you can use it as a formula triangle if you'd like. So let's do a little triangle. And that'd be F, K, E. If we're covering up K, then it's going to be force over extension. Or if you're a bit more mathematically inclined, you can just rearrange this formula by dividing both sides by E. But either way, the way you're going to do it is you're going to take the force, 300, and you're going to divide by 0.4. And that's for 3 marks. Like, that's not bad at all. So 300 divided by 0.4 gives me 750. Now, of course, you need to remember the units, but in this question in particular, they've given them to you. So it's even easier. 3 marks, in my opinion, not that bad. The rearranging is obviously the part that's a bit tricky. And yeah, if you, with this question, if it's on your formula sheet, then you can just use that, of course. So just keep that in mind. Be open to reading that formula sheet. For question 2, we have professional rugby players wear a tracking device that measures their velocity and acceleration. Figure 2 shows a player wearing a tracking device, so right here apparently. The player is tackling another player is running with the ball. Velocity and acceleration are both vector quantities. What is a vector? So is it a quantity of both magnitude and direction, or only magnitude? So first of all, this is none. That is not a vector or a scalar. The only question is whether or not it has direction or not. Okay, so scalars are only size. So they are only magnitude. So things like time, right? When I say like 1 hour, I don't give you a direction, do I? I just say 1 hour. When I say how much I weigh or how much mass I have, if I said 80 kilos, I'm not giving you a direction with that. If I give you my speed, 50 miles an hour, there's no direction. You can't tell which way I'm going. You just know how fast I'm going or how heavy I am, okay? Or how much time it took. With a vector quantity, it has magnitude and direction. So for example, if for me to change my speed to velocity, so when I said 50 miles an hour, if I said 50 miles an hour heading west, that is now a velocity because you can tell which direction I'm going in. Okay? With the mass, well, technically you'd have weight, which is a force. Forces always have directions, right? Weight always points down, that is a direction. Or you could have something like friction that goes opposite to wherever you're moving, that's a direction. But that's the general idea, okay? So just think about whatever quantity you have, if it has direction. If it does, it's a vector. If it doesn't, it's a scalar. Then it says for part 2, which of the following is a vector quantity? So let's go through them one by one. So displacement and distance are effectively scalar and vector forms of each other. Okay? Now displacement is distance in a given direction. Okay? That's the key thing. So the example I like to use is, imagine this is me. As you can see, 1-to-1 recollection, although I haven't got the hair right, of course. And let's say I walk this way and then back. Now let's say that distance is 1 meter. The distance I've travelled is 2 meters, right? 1 meter to the right and 1 meter back to the left. But what's my displacement? Well, displacement is distance in a given direction. It's the total how far away you are from your starting point. So I've gone 1 meter away and then 1 meter back, How far away am I from the starting point? 0 meters. Okay? So displacement is a vector, whereas distance is a scalar. It only gives a size. Okay, now what about time? Well, again, I don't have any metric for saying which direction I'm going in time. Okay? Work done. Work done is the same as energy. Energy has no direction. It's just a size. I have 100 joules of energy. Okay, I don't say I have 100 joules going that way or going this way. It doesn't make a difference. Now, some of you might say, but work done is force times distance. Doesn't that give me a direction? No, because distance is a scalar quantity. Okay, so it doesn't actually give you a vector quantity. Okay, so hopefully that makes a bit more sense with vectors and scalars. Just think about direction, direction, direction. If there is a direction, then you have a vector. If there isn't a direction, then you have a scalar. So for the next two parts, we have a velocity time graph, and it's really important you make sure you know it's a velocity time graph for the player running with the ball. And as you can see here, it goes up, then stays flat, and then it goes down to 0. So what is this describing? Well, it's velocity. So if velocity is increasing, that means at this point, the player is accelerating. So she's speeding up. When it's flat, it doesn't mean she's stopped. It means she's traveling at a constant velocity. So she's reached, let's say, her peak speed or velocity, and she's maintaining it. Okay? So again, it's like going onto a motorway, if you've ever been in a car with your parents, right? As they go onto the motorway, you feel the acceleration, you pull back, because they're speeding up. And then when they reach whatever speed, so probably 70 miles an hour or 60 miles an hour, they maintain that. That is a flat line on a velocity time graph. This bit at the end, we can probably imagine what's happening. If we go back to the original picture, that's when the players collide with each other, right? Because all of a sudden, in a very short space of time, it looks like 0.2 seconds, she's going from traveling at 4 meters per second to 0. So, slammed into each other, which is pretty funny. But anyways, to determine the acceleration of the player. So, with a velocity time graph, there's two things they can ask you to work out. Acceleration and distance traveled. The distance traveled is velocity times time, isn't it? It's the area under the graph. The acceleration is velocity divided by time. So it's the gradient of the line. So all you need to do is mark off these 2 points. So that's 1.6. So all we're doing here is we're taking the change in the y-axis, again, bit of maths. So it ends up at 4, starts off at 0, so it's 4 minus 0, over, ends up at 1.6 seconds, starts at 0, so 1.6 minus 0. So let's work this out. So of course, since we're minusing 0, I don't have to worry about that. I can just do fraction 4 over 1.6, but let's type it in fully just to make sure we're all on the same page. 5 over 2, which is 2.5 meters per second squared. Does it give me my unit? It does. Makes my life even easier. So here it says, describe the motion of the player between 3.4 and 3.6 seconds. So what does that mean? What does describe motion mean? With a velocity time graph, you're going to say this. You're either going to say accelerating, decelerating, or constant velocity. Okay? Those are the three things you're going to say. Now, with the accelerating and decelerating, you need to say if it's constant or not. So is the gradient constant? I.e., is it a straight line? If it's a straight line going up, that's constant acceleration. If it's a flat line, constant velocity. If it's a straight line going down, constant deceleration. If it's curved, you would just say not constant acceleration. Okay? So in this case, it's a straight line down, so it's going to be constant deceleration. Hope that makes a bit of sense. And here we have the force exerted on the player when she is tackled causes her to accelerate. Write down the equation which links acceleration A, mass M, resultant force F. This is your boy Isaac Newton's equation. It's one of his laws of motion. It is the second law of motion. F equals ma. If any of you are doing A-level maths or A-level physics, this is going to be your bread and butter. This is going to come up a hell of a lot, okay? And in part 6, we get to use the equation. How lucky for us. So it says the player accelerates at 25 meters per second squared. When a resultant force of 1800 newtons acts on her, calculate the mass. So again, I'm going to draw out. I mean, first of all, you could just rearrange the formula. So m is equal to F divided by A. But for those of you that like the formula triangles, I know there's a few of you, let's do it this way. It'll be F, M, A. We want mass, so it's force over area. If you noticed in both parts, you had, for question 1 and question 2, we've had to rearrange this formula. So again, if you're unsure about rearranging, now will be a really good time to just practice rearranging or writing out formula triangles for these kinds of equations, okay? The reason why I've written it like this is because it's MA. I know that has to be on the bottom because that's where times is. Anyways, so force over acceleration. So we have 1,800 over 25 gives me, again, let's be nice and lazy, 1,800 divided by 25 gives me 72 kilograms. Again, 3 marks. Hopefully not that bad. And for the last part, this is a bit of an like a nebulous question. So they like to throw some of these in where they're not really related to science per se. It's more about your ability to apply things to real world situations. So it says the tracking device sends data to a computer during the game. It's just an advantage of the data being sent during the game. So yeah, it's a bit tricky, but think about what it means by sent during the game. It means that there is a live feed of data, right? So you can check the data during the game. So check data during the game. That's my kind of logic that I would use. During the game. Okay? You can also say things along the lines of it doesn't have to be downloaded afterwards or anything like that. You don't have to wait until after the game to get information on the performance. You can make changes during the game. Any of these are also accepted. For the next question, we have a student makes water waves in a ripple tank. Describe how the frequency and wavelength of the water waves in the ripple tank can be measured accurately. So here we have 2 kind of components to our answer. We're going to talk about the wavelength first, and then we're going to talk about the frequency. So let's start with wavelength. Now, let's think about this actual experiment. When you make waves in a ripple tank, this is roughly your experimental setup. So you're going to have something that's oscillating in a body of water. And what you want to do is you want to set up a ruler. That is a horrible drawing, good lord. You want to set up a ruler along the side of the tank. Like that. And you have your ruler along like this. And what you're going to do is measure the distance between 2 of these peaks. Now, what is this actually going to look like when you do the experiment? Because obviously you won't see this weird blue looking water. Well, it looks something like this. What you'll have is these dark patches and light patches. So all you need to do is measure the distance between 2 light or dark patches. And this is literally where the water goes up and goes down. Because as you know, the water is going to be traveling like this when there's a ripple. And you can see ripples. So how exactly are you going to do this? Well, what you want to do is actually set up a camera that's going to look down at this setup that you have here. And you're going to have the ruler along the side in order to measure the actual distance. Okay? Because of course this is actually happening in real time. It's very hard to measure that in real time. So instead you're going to use a camera to take a picture, and then you're going to literally just measure the difference between these 2 spots. So let's actually write out what we're talking about here. So what you want is you want to have a meter ruler along the side of the tank. You can also describe this as perpendicular to the actual wavefront itself, but you don't really need to say that. And then what we're going to do is, using a camera, so take a top-down picture and use the ruler to measure the distance, and you can just call them between peaks, okay? Between peaks. And that is your wavelength lambda, okay? Now what about for frequency? Well, this is where it gets a bit more interesting. There are a bunch of different ways to work out the frequency. And again, if you looked at the mark scheme for this question, you might notice that my wavelength method isn't exactly what it says on the mark scheme, but it is one of the alternative methods anyway. So there are multiple different methods of doing this. Now for the frequency, I like to think about what the frequency is. The frequency simply tells you how many full wavelengths are going past each second. So for example, if I were to mark a point here and count how many waves, so how many peaks go past this point every second, that is my frequency. And that's exactly what we're going to do to work out the frequency. Okay, so again, each peak that passes this is going to increase the frequency. So all we need to do is count how many kind of go past it. Another thing you can do, now of course, to make it accurate, we don't want to just do 1 second. Because imagine yourself with a stopwatch and you go, tick, tick. That's, it's very hard to keep track. So you can either measure for 10 seconds how many waves go past that point and then divide the answer by 10 to get the frequency. Because in 10 seconds, let's say you get 15 waves. Then you do 15 divided by 10. You get 1.5 waves per second, which is your frequency. The other thing you can do is use this camera you set up earlier. Most cameras, especially the ones you use in experiments, have timers on them. So you can literally just play it for a second in slow motion and count how many waves pass that point. Either one of those is completely fine. So I'm going to choose the latter option. So play video in slow motion. And count how many waves pass a given point. That is your frequency. So the question is, where do you get the fourth mark if I've already done 3 bullet points? Well, it's some measure of maintaining accuracy. So for example, using video instead of a stopwatch is a way of maintaining accuracy. So you can also mention things like taking photos of the setup. So take photos to reduce uncertainty. But that should give you the 4 marks, and I hope that makes a bit more sense. The student recorded values for the frequency and the wavelength of waves in the ripple tank, and table 1 and 2 are showing the results. So we had the frequency in hertz and the wavelength in centimeters. And it says determine the mean wave speed. So what you want to do is get out your kind of formula sheet and locate the equation for mean wave speed, and it is simply F lambda. You sometimes see it as written as C equals F lambda. Either one's fine, so we're just going to find the frequency, multiply it by the wavelength. Now remember, wave speed is in meters per second, and I've noticed already that this is in centimeters. So when we work out the mean, we're also going to have to convert it into meters as opposed to centimeters. So let's do the mean frequency. So call it mean F. How do you work out the mean? That's a brilliant question. Well, again, if you remember some of your kind of GCSE maths knowledge, you add them up and divide them by the number that you have. So we're going to do 9.8 plus 9.4 plus 9.3. So 9.8 plus 9.4 plus 9.3 over 3, and that should give you an answer of 9.5 hertz. With the wavelength, you're going to do the same thing. Whether you convert first or you convert afterwards shouldn't make any difference. So 1.7 plus 2.2 plus 2.1, and then we'll change it into meters afterwards. So if we add those all up and divide them by 3, we get a nice even 2.0 centimeters. Now how many centimeters are in a meter? 100. So if I divide that by 100, you should get 0.02 meters. Which means last but not least, you just need to now sub it into the formula we have back up there. 9.5 multiplied by 0.02 gives you an answer of 0.19 meters per second. Again, these calculations, they're worth a lot of marks and they're not that bad. So I'd recommend, once you get in the exam, if you get stuck, just try and work some stuff out, okay? Try and work out means, try and work out frequencies. Use any equation on the formula sheet to try and scrape together some marks, because it's really easy to get marks, okay? Questions might not be easy, but you can gain some marks. One is better than none. Part 3, this is testing your experimental knowledge. What is the advantage of taking repeat readings and then calculating a mean? And this is really important. If any of you want to do any science at A level or in the future, in university or in a job, every single human being on the planet that does science takes repeat readings. And there's basically 2 reasons for this. Now, one is the reason that they're kind of looking for, which is it reduces the effect of random errors. So reduces effect of random errors. However, there is another accepted answer. So by the way, with random errors, what does that mean? Well, random errors are ones you can't predict. So if you do an experiment once, how do you know you haven't had any random errors? Right? So for example, if you didn't know what a dice was at all, and you rolled it once and the number 3 popped up, if you draw a conclusion from that, you would say, okay, every time I roll this dice, I'll get a number 3. But how do you know? Instead, the only way to actually verify that is to do it again and again and again and see what happens multiple times. Okay? And this is true for pretty much anything in life. Doing something once doesn't mean that it will happen every single time. Okay? So, reducing the effect of random errors, you repeat and then you can compare the results. So what's the other reason that you can use, which they're talking about? It also allows you to discard anomalous results. How can you tell if a result's anomalous if you don't have other readings to compare it to? You can't. So either one of those answers perfectly fine, but I wanted to also give you the knowledge of why that makes sense. Now here is actually one of my favourite styles of questions in physics, because once you know the technique, you don't need to know anything about science to get the marks. So here it says the speed of the wave is affected by the depth of the water in the ripple tank. The deeper the water, the faster the wave. Explain how the depth of the water affects the wavelength of the wave if the frequency is constant. They've given you the answer in this question. And I'm not saying this to make you feel dumb. I'm just going to show you a really interesting trick. Now, physics is all about maths and interpreting it. So it's all about equations. So they're telling me the speed of the wave is faster in deeper water. Okay? Now, what equation did we just use? We used V equals F lambda. This isn't part of my answer, by the way. This is more like an explanation. I'll show you the 2 bullet points that you need for the answer. And they say that F doesn't change. So, somehow V is bigger despite the fact that F stays exactly the same. What's the only possibility? Lambda must be bigger. It has to be. Because if F is the same, but V is bigger, lambda must, or wavelength, must give you that extra bit. So if I said the velocity doubles, but the frequency is the exact same, logically, the wavelength must double. Because that's the only way the velocity could have increased. So that's all you need to say. And again, we've used the equation right here, and they've basically given you the answer. The speed increases, but the frequency is constant. The only option is the wavelength increases. So all you have to do is literally, basically, rewrite the question. So you say deeper water increases the wavelength, because as we've just discussed, that is the only way for velocity to increase. So deeper water increases wavelength, which of course you can't just write lambda, unfortunately. And then why? Because V increases and F is constant. 2 marks. And all I've really done is read the maths, read the equation. And they told me all of the information I need to know. Deep water increases wavelength. How do I know that? Well, because V increases despite frequency being constant, so lambda must increase. That's it. Okay. Hopefully that makes a bit more sense. I hope so anyway. But again, if you have any questions, leave them in the comments and I'll get back to you. Magnets. Everyone hates magnets, and honestly I don't blame you. They're very nebulous. In fact, I was in my 4th year at university by the time we actually got to learn about magnets in full. So it's a very advanced topic, so it makes complete sense that you're a bit worried. So, Figure 4 shows the magnetic field pattern around a permanent magnet. Where is the magnetic field of the magnet strongest? You can either memorize this, but I'm also going to explain it to you. Now, it's at the poles. So if you're okay with that, feel free to skip to the next part. But if you're not, here's why. When you have a field pattern, whether it's gravitational, electric, or magnetic, the closer together the lines, the stronger the force. Okay? In other words, the more lines you have, the stronger the force. If I look at the poles, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 lines here. If I look at these parts, there's only 3 and 3. Which means, at the poles, it's over twice as strong. That's literally all it is. That's why field patterns are so useful in science. And you'll find this with electric, gravitational, and magnetic field lines. The closer they are together, or the more of them there are, the stronger the force. That's all you have to remember. So you're just looking for wherever there's the most number of lines, which is at the north and south pole. And part 2 basically piggybacks on what I just said. How does figure 4 show that the strength of the magnetic field is not the same in all places? Well, as I just mentioned, the closer together the lines, the stronger the force. These are not just equal distance. Can you see that they get further apart as you go away? That's literally all you need to say. The distance between field lines changes. That's it. Figure 5 shows an electromagnet being used to separate iron and steel from non-magnetic materials. Explain one reason why an electromagnet is used instead of a permanent magnet. Now, electromagnets are one of the most important inventions in recent history. Without them, we wouldn't have things like speakers and microphones, which use electromagnets to produce sound. They literally vibrate a metal plate. That's literally how they work. So, why do we use an electromagnet instead of a permanent magnet? The clue is kind of in the question. Permanent magnet, electromagnet. Well, given that there's a difference, one of them can be turned off, which is really useful. A magnet that's always on, it's not the most useful thing in the world, because, you sometimes want it to be off, right? Like sometimes you want to take stuff off of the magnet, for example. So, first one is that you can simply say the electromagnet can be switched off. And again, if you didn't know anything about science, you could deduce this, right? Why would they call one of them a permanent magnet and one of them an electromagnet? Well, the electromagnet must not be permanent, right? There's no point in calling it permanent if the other one is also permanent. So one of them must be able to be switched off and it must be the electromagnet, okay? So again, no science really involved. So electromagnet can be turned off. That's fine. Now, let's think about why you would want a magnet to be turned off. Because if you look here, it's trying to take iron and steel from non-magnetic materials. So why would we ever want to turn that off? Well, okay, let's just think. Have you ever used a permanent magnet and then you stuck something to it and then it's hard to get off, right? And, I growing up, my dad had like really strong magnets. I can't remember the reason why. But every time we got stuck to like the radiator or something, it was hard to pull off. Well, that's why we want to be able to turn it off. It's so that we can get rid of the metal that's attached to the electromagnet. The whole point is to get the iron and steel out from this material so we can recycle it. But could you imagine having to try and rip it off of the machine? That just takes too much effort. Instead, if we can just turn it off, it just drops it. That's way easier. So simply, it's easier to remove the iron and steel. Or you can say the separated metals, by the way, just FYI. So I hope that makes a bit more sense. At least one mark, I hope, can be a bit logical. I'm hoping I'm teaching you some exam technique here. Okay, try and, deduce it. Get your Sherlock Holmes on. Try and scrape together some extra marks, because it's the difference between grades. And this question is kind of common knowledge, I'm afraid. Pieces of iron and steel are attracted to the electromagnet. Name 2 other metals that would be. So the ones that you might be aware of are nickel and cobalt, which, by the way, is why things like, the kind of bronze coins like the 1 and 2p's are attracted to magnets. It's because they're actually made out of nickel mostly, hence they're magnetic. But some other ones that you could say, if you're a bit fancier, are, and by the way, these aren't in the mark scheme, but what happens is when examiners get the mark scheme, there's a certain understanding that they know enough about science to know some other kind of magnetic materials. So you could also have platinum. Neodymium is actually a pretty common one. It's in a lot of electronic devices. You also have titanium and gadolinium, and also bismuth, which is kind of interesting. It doesn't sound like a metal, does it? But those are kind of the other ones you could have. But these are the most common that you may have come across. Nickel, I'm hoping you have. Anyways. So in this part, they say the design of the electromagnet cannot be changed. So they're giving you a bit of a restriction here. Give 2 ways the force exerted by the electromagnet on a piece of iron or steel could be increased. So if they gave you full reign, you might say something like, give it a soft iron core, wrap more coils around the electromagnet, something along those lines. But they're saying the design cannot be changed. So what else can you do? Well, the other 2 things it's affected by, the first one is increase the current. Now, in this actual exam, the second one was very difficult because it's not in textbooks. Okay, so again, the other things, soft iron core, etc. All of those standard ones. But they're saying the design cannot be changed. So the other one was a lot trickier for people to kind of come up with. Now, as with all forces, magnetism gets weaker with distance. So this probably makes sense now. If you ever thought about using a magnet, it doesn't attract everything from everywhere. You have to bring it closer and closer until the object starts to move towards it, right? Because with distance, the force gets weaker. So simply move the electromagnet closer to the iron or steel. In my opinion, that's a bit of a cheap mark, but a lot of people did not get the second mark at all. But hopefully it makes sense now. Again, think outside the box in certain questions, okay? Here we have the motor effect, or the generator effect. Simple motor, you've probably seen this before, but you're probably starting to panic now because this gets a bit tricky. And if we go down, we have a 5-mark calculation. However, I want to point out it's not that bad. Of course, if you're struggling with magnetism, it is bad, but think carefully. They've given you, I write down the names of the variables. So they give me length, they've given me current, and they've given me force. So what I would look at on my kind of formula sheet is look for an equation that has F, I, and L in it. And if you're kind of on it, hopefully you know that magnetic flux density is B. So you're looking for an equation which has F, I, B, L in it. And there's only one on your formula sheet. In fact, there's only one for F, I, L, I'm pretty sure. So you should find force equals Bill. And then you're just subbing in the numbers they give you. But again, put it in standard units. So millimeters is no good. We need to change it into meters. So all we have here is the force is 0.36. Magnetic flux density is what we want. Current is 4. And 120 millimeters in meters is 0.12. And then all you need to do is, if we sort this out, 0.36 equals 4 times 0.12 is 0.48 B. So then B is just equal to 0.36 over 0.48, which would give you 0.75. And then the unit, which is another mark. So you actually get a mark for the answer and a mark for the unit. And then it's 3 marks just for this. In terms of maths, it's really not that bad. But again, if you're confused, if you're scared because of all these other science words, just write down the variable letters and then look on your formula sheet. It's your best friend in this exam, okay? 5 marks is a huge amount for a relatively easy calculation that you have a calculator for anyway. Okay, I'm not trying to put you down. I'm trying to say, use that formula sheet to work out which equation they want you to use. Even if, I remember once I went into a science exam and I didn't know what the hell they were talking about on one of the questions. And I used, this is one of my mocks by the way, not my final exams, but I used the formula sheet they gave me and worked out the equation and got the answer right. Okay? It was pure guesswork. I'm just very good at kind of being lazy, as you guys can probably tell, but hopefully that makes a bit more sense. Here we have the good old-fashioned Fleming's left-hand rule, which is why people start throwing up gang signs in their science exams, and we just need to complete the figure. We don't actually have to use it, which is kind of nice. Now, how do you remember which one's which? Practice, but obviously that's not very useful a couple of days before the exam. So what I do is I think of what the fingers are called. So I'm going to try and show all of my fingers. This is called my first finger. First finger field. So it's the direction of the field. What kind of field is it though? It's a magnetic field. So again, first finger field. So first finger field. That's how I remember that one. Now what about this middle finger? Well, it doesn't begin with M. It's also my second finger. Do you see the C in second? So second finger is current. Now, what about the thumb? This one isn't going to make much sense to you guys. It might do to a few people who've been taught by physics teachers like my physics teachers. But the thumb is TH, right? If you underline that, that stands for thrust, which is the same as force. So, yeah. How about, for those of you that don't use this weird way of remembering it, how else can you remember it? Well, if you know that there's field and current, for first finger current, second finger, first finger field, second finger current, the other thing is just the force, okay? I don't know if that really helps, but at least for those two, hopefully it does. But yeah, that's essentially how I remember it, other than just practice and a lifetime of doing physics. Here we move on to the radiation/visible light thingy part of your spec. So different parts of electromagnetic spectrum are used in medical imaging. So here we have an image of a person's hand with an infrared camera which measures, shockingly, infrared radiation, which is associated with heat, so how hot and cold different parts are. So as you can see here, so by the way, just as like a behind the scenes, when you see something like this, the hot parts are actually good because that means there's a lot of blood flow. This person here has lack of blood flow to his two fingers here. And you can tell that because if you look, this is about 23 degrees. These are 34 degrees, 11 degrees hotter. So that's really not good. The person probably has lost circulation in two fingers completely. Anyways, so explain why the infrared camera is able to show that different parts of the hand are at different temperatures. Well, again, I mentioned before that infrared radiation is associated with heat. The hotter something is, the more infrared radiation it gives off. Okay? That's pretty much the basis of our answer now. So different temperatures emit different intensities of infrared radiation, so of IR. And this is represented as different shades. Cool, that's it. Part 2, infrared has a range of wavelengths from 700 nanometers to 1 millimeter. Which part of the electromagnetic spectrum would have waves with a wavelength of 6.5 times 10 to the minus 7 meters? So you might notice that this is actually 650 nanometers. The reason why I say that is it's very close to infrared radiation, but it's a slightly shorter wavelength. So what you need to think about is on your kind of electromagnetic spectrum, which one is just a shorter wavelength than infrared is actually visible light. Generally, if you have a times 10 to the minus 7 and it's below 7 times 10 to the minus 7, it's going to be visible light, okay? So hopefully that makes sense. For part 3, we have X-rays and gamma rays being used for medical imaging. So we have an X-ray here, gamma ray over here. To use X-rays for medical imaging, a machine produces a very brief burst of X-rays, so it doesn't last very long. To use gamma rays, a radioactive isotope is injected into the patient's blood, the isotope is circulated around the body, and the isotope is continuously emitting gamma rays. Compare the potential risks to a patient of using X-rays and gamma rays for medical imaging. So, as you may be aware if you've ever had to get an X-ray, X-rays and gamma rays are both dangerous. So that's exactly what we're going to say. So, X-rays and gamma rays. Now, when I say it's dangerous, why is it dangerous? Right, it's only an X-ray, right? You can't even see it. Well, the reason is it's ionizing radiation, which means as it penetrates your body, it's going to start ionizing bits of your DNA, which can cause mutations, which is basically what cancer is. So, X-rays and gamma rays have a risk of cancer. Okay? So they both have that risk. Now the question is, which is kind of worse, X-rays or gamma rays? Well, if we actually look, they've given us a little bit of information. First of all, very brief burst of X-rays. That implies it's very quick. Whereas with the gamma rays, it doesn't say it's brief. In fact, it says the isotope is circulating around your body. You can imagine that takes longer than just a flash. If you've ever had an X-ray, it literally is like taking a picture. It's very, very quick. So, all we have to say is X-rays have a shorter exposure than gamma rays. So that means it's like a lower risk in that sense. And what was the other thing I said? Well, with an X-ray, they generally only take a picture of part of your body. Maybe your leg, maybe your chest area or something like that. With gamma rays, it goes around the entire body, which means you're being irradiated through your entire body. So gamma rays spread through, or irradiate your entire body. Whereas X-rays irradiate a small part. Irradiate a small part. That's it. 4 marks. Not too bad. I will say that you can kind of extract this information from the text if you read quite carefully. But again, some real life knowledge and obviously that handy CGP book has probably helped you out with that one. X-rays are produced by colliding high energy electrons into a metal target. The electrons have high energy because they're accelerated to high speeds. Only a small proportion of the kinetic energy of an electron is converted into an X-ray when it collides with a metal target. An electron is accelerated at a distance of 15 millimeters, and the work done is 1.2 times 10 to the minus 13. Calculate the force. So again, what we're going to do is we're going to label D. This is work done, so W, and the force is obviously F. So you're looking for an equation that has F, W, and D in it. And hopefully you come across the work done formula, which is work done is equal to force times distance. And we're trying to work out force, so that would be work done over distance. So work done is 1.2 times 10 to the minus 13 joules. And what about the distance? Well, it's 15 millimeters. So if we divide that by 1,000, we should get kind of the value that we want, which is 0.015. So divide that. Whoops. That damn E button. 0.15. And let's whip out our calculator. We have 1.2 times 10 to the power of negative 13 over 0.015 gives me a value of 8 times 10 to the minus 12 newtons. That's it. So in the previous part I mentioned that they use tungsten as the metal for the target. Now tungsten has the highest melting point of any metal. So why would using tungsten enable the X-ray machines to be more powerful? Well, this comes from the fact that as you collide with things, you produce heat. So if you kept punching a wall, you would eventually start heating up the wall itself. Every collision transfers kinetic energy, and kinetic energy is heat energy. So, enables the machine to be more powerful. So what they mean by that is you have more energetic X-rays, right? Which means you need to slam those electrons into the metal target harder and harder and harder. Now, if your metal has a low melting point, the metal will begin to melt, the target will melt, and it will be damaged. So that means the machine won't work. So that's why if you use tungsten, you'll have a very powerful machine, because it can withstand those collisions. So, electrons colliding with target cause heating. Cause heating, which increases the temperature. And so you need to have a metal with a high melting point. So a high melting point allows more energetic collisions. This question, I'm actually going to write the answer along the side because I think it will make my handwriting a bit easier if I'm not actually using my handwriting. But scientists are developing a hypersonic aeroplane, so faster than the speed of sound, that will travel much faster than normal aeroplanes. An aeroplane accelerates from a low speed to a high speed with the engines at maximum power, but why is the acceleration not constant? So, this is a really good question. So when you have the engines at maximum power right at the beginning, I'm going to draw a plane as just a box. There is just the forward force of the engine, and that's like right at the beginning. However, as this object, this plane, starts to speed up, it's hitting the air with more force, which means there's more air resistance. So this air resistance, which is this way, I'm going to call it FR, begins to get bigger and bigger and bigger and bigger. Now what that means is the actual resultant force, the overall force, is changing. And remember, resultant force is equal to mass times acceleration. So if there's a resultant force, it means there's an acceleration. So all we have to do is the forward force is constant, right? That engine force is always going to be constant. However, as the plane accelerates, the air resistance increases. The resultant force is equal to the forward force minus air resistance. So over time, resultant force decreases. F equals ma, so the acceleration decreases. That's exactly how I'd write it. So it's not really that many words. So just go over it again. Right at the beginning, as soon as the engine turns on, you have this massive force from the engine pushing the plane forward. However, as this plane speeds up, air resistance gets bigger and bigger and bigger. Now the resultant force is just the difference between those two forces. So you take this forward force and you subtract this resistive force, the air resistance. Now because the air resistance is getting bigger, the resultant force is getting smaller, which means the acceleration is changing over time. So hopefully that makes a bit of sense. So always relate things back to kind of F equals ma when you talk about forces. Here we go. So we have a hypersonic aeroplane that has jet engines. I've read the marks. So we have 6 marks in total. Jet engines and a rocket engine. Now the speed of airplanes tends to be used as the Mach scale in terms of speed, and it literally is just how many times the speed of sound you're going. So Mach 1 is the speed of sound, Mach 2 is twice the speed of sound, and so on. The jet engines will accelerate the airplane to Mach 5.5. The rocket engine will go from Mach 5.5 to 25.5 in 300 seconds. The average resultant force is going to be 630,000 newtons. Calculate the mass give you answer to two significant figures? Well, remember what I said. F equals ma is what we're going to be using for this equation. Because if you ever have force and acceleration and you want mass, that's F, M, and A. So you're using F equals ma. Okay, so it's always going to be the same. Now, what do we have? Well, we have the force. The force is 630,000 newtons. The mass is what we want to work out, so we don't have that yet. And the acceleration we don't have. So we're kind of screwed. However, think about it. What is acceleration? It's the change in velocity over time. So it's the change in velocity. So all we need to do is use this as our change in velocity. Now, keep in mind that we probably want to actually work this out in terms of meters per second. So V minus U is just 25.5 minus 5.5, which is 20, or Mach 20 I should write, but 20 Mach is what I want to have for now. To change that into meters per second, which is what we want, we do 20 times 330, which is going to be 6,600 meters per second. So add on a 0 and double it. So the acceleration now is going to be 6,600 over 300 seconds. Okay? So cancel those out. That gives us 22 meters per second squared. Okay? So now we have F equals ma, we have F and we have A. So all we need to do is rearrange that formula. Again, if you want to use the formula triangle, let's draw it out for you. And we're going to have, God, that's absolutely terrible. F on top. We have M on the bottom and A. Cover up the mass. And we're just doing force divided by acceleration. Or if you want to rearrange it, just divide both sides by A. So we're just doing mass is equal to force over acceleration. So that's 630,000 over 22. So get out your calculators. So, boom, here we go. 630,123 over 22 gives me two significant figures. So we have, I'm going to write out the full number first. Well, I'm not going to write out the decimal points because I'm lazy. kg. Then to two significant figures, you go to the second number along. So 1, 2, underline it. Look at the number next to it. If it's 5 or bigger, you round up. You make the number we underlined 1 bigger, and then you just replace everything with 0. So 29,000 kilograms to 2 fig. And that brings us to the end of the paper and the end of most of your GCSEs. So most of you are going to be finished after Friday, after the physics exam. However, I know some of you have like food tech and further maths, things like that. But yeah, best of luck with the exam. Again, in the comments, leave any questions you have and I'll get back to you. I love physics. It's my jam. I could talk about it all day. But yeah, I hope this was helpful and best of luck.